Hello, everyone. My name is Dr. Minoo Rathnasabapathy, and I'm representing the Space-Enabled Research Group at the Massachusetts Institute of Technology's Media Lab. Welcome to the 6th High-Level Industry Science Government Dialogue on Atlantic Interactions and Technical Sessions. These technical sessions focus on innovation for sustainable marine development and the blue economy, hosted by Penn State's Alliance for Education, Science, Engineering, and Design with Africa, and co-organized by the Air Center. Today's plenary begins with thought leaders from Air Center's member nations and international scientific research community, as well as industry partners, to discuss ideas, initiatives, and projects around nanosatellite constellations for improved environmental and maritime security, such as monitoring maritime terrorism, piracy, trafficking, illegal fishing, environmental crimes, and maritime disasters. Now, we know that satellite technology plays a pivotal role in addressing some of these key challenges, making it possible to map regions and pinpoint vulnerable areas. It also helps identify weaknesses and develop actionable steps, both to prevent and address old and new threats. Each panelist will present for approximately 10 minutes each, after which we will have time for audience Q&A. You should be able to see a chat window on the right side of your screen, so please submit your questions because we want to hear from you. So let's kick off our panel. Our first speaker is Amal Khatri, the Executive Director of Space Programs at the South African National Space Agency. Amal, thank you so much for joining us today to talk about South Africa's indigenous capabilities in maritime domain awareness solutions and the opportunities presented by nanosatellites. Amal, over to you.
Thank you very much, Minnie. I'm going to share my screen, so just give me a second. There we go. Okay, let me know when you can see my screen.
We see your screen, yep. Amal, go ahead. Perfect.
Okay, fantastic. Yeah, so we've got 10 minutes. I've got to get through 120 slides, so it's going to take a bit of a challenge. Just kidding, I've got a few less slides than that. So I'm going to talk a little bit about South Africa and particularly the maritime domain environment. So I think, you know, when I chat to colleagues and we speak about Africa, quite often we're quite surprised that most people don't really understand the extent of Africa. If you actually look at our coastline, it spans 3/4 of the circumference of the Earth. In fact, 22% of the Earth's land surface is Africa. There are 38 African countries, are coastal or island states. I think what's important to note, and if you look at the sort of picture on the right-hand side, and you've probably seen this around, that if you take a number of different countries and you put it into Africa, you can actually understand how huge Africa is and why satellites start to play quite an important role in terms of managing our resources. So as part of the African Marine Domain Awareness, a strategy has been developed. It's the 2050 African Integrated Maritime Strategy. And I think the importance of this is really focusing on the fact that, you know, ocean economy is critical. We need to understand the inland waters. We need to understand the pressure of climate change and the impact it's having on our African continent. To a large extent, in fact, 90% of Africa's import and exports are conducted by the sea. So if you think about the African marine challenges, you also need to consider the African Space Program. So there is an African Space Program. There are two important elements to it. It's the African Space Policy and the African Space Strategy. Recently, We have established essentially the African Space Agency, and these are important elements of cooperation to ensure, from an African perspective, there's a great deal of collaboration and partnership. Now, out of the 40 AUC objectives, in fact, 35 of these are serviced by space application. Now, if I just zone into South Africa at the moment, to address these challenges, South Africa launched what we call Operation Pakisa. And Operation Pakisa is essentially 5 focus areas: marine transport, manufacturing, offshore oil and gas exploration, aquaculture, marine protection services, and coastal tourism. And in my discussion, we'll try and highlight why satellites becoming important in this area. So I want to dive right into the fact that it's not really about satellites, right? At the end of the day, it's actually about the decision-making tools. It's like the user case. Why exactly are we building satellite constellation? What are we trying to achieve out of this here? So from a South African perspective, for us, maritime spatial planning, coast flood hazards, harmful algae bloom, water quality, the sea state are critical elements, including marine domain awareness. So part of the cooperation with the Council of Scientific and Industrial Research in South Africa, we've developed what we call the platform is called OCEANS. It's the National Oceans and Coastal Information Management System. And I just want to emphasize, about space missions. We as engineers, we want to do all cool things, and we love, new technology. But at the end of the day, we have to meet the user requirement. Why are we investing in certain technologies? And in Africa in particular, with funding challenges, it is important for us to get this absolutely correct. So here's an example of OCEANS. This is the vessel tracking environment. 2 critical elements of OCEANS is your satellite-based automatic identification system and Earth observation. This could be an optical payload, or it could be a SAR payload, for instance. On the left-hand side, you'll see a picture of vessels that are being tracked. Further to that, in the marine domain awareness application, we are working in 2 areas. One is AIS, and the first couple of space missions that we are developing is on automatic tracking of vessels. And we know the importance of this here. There's a lot of vessels in the sea that shouldn't actually be there. And satellites obviously play a pivotal role. But we're going to be moving over eventually to VDAS. And really, this is looking at a technology that creates higher bandwidth. We'll have maritime machine-to-machine communication ships between ships and shore, ships and satellite. And now we're talking about the 4th Industrial Revolution, in fact, right? We're talking about integrated system of many different devices talking to each other to manage our marine environment. So just in terms of our capability, we have developed several satellites. Our first launch was in 2013. This was Africa's first. We launched a satellite called ZAQ-1. Subsequent to that, we launched a second satellite, ZAQ-2. This was launched on the 27th of December 2018. This was launched as a demonstrator. In fact, it's quite interesting. The ZAQ-2, we managed to pick up a vessel that we couldn't identify in the ocean that was actually transporting narcotics. So, just a demonstration satellite, and we already got a benefit out of it. So in terms of the mission roadmap, where we're going into the future, this is obviously ZAQ-2, what we launched in 2018. The next phase of our program is 3 satellites. This is the Marine Domain Awareness Satellite 1 constellation. And the whole intention of constellation is really, you need real-time information. You need to see more, right? You need to get information available that can allow you to make decisions quickly and timely. Then the next phase after that would be the 2022 to 2023 phase, where we're looking at developing a constellation of 9 satellites with full VDAS capability. Now, the importance of a constellation of this nature is that because satellites are orbiting the entire planet, this type of data becomes available broadly to other user communities as well. So I think what's important to understand, and I'll be concluding my presentation soon, is that we need to start thinking, particularly in Africa, we're starting to look at multi-purpose, multi-sensor approach to nanosatellite constellation. And the intention behind this is, how do we develop satellites, whether it's a 3U configuration or bigger, how do we develop constellations that can enable us to have or derive value out of it, right? So can we have several payloads on a nanosatellite constellation to do many interesting things that meets our user requirement? So just to touch on this briefly, in terms of the value, if you look at this particular graph, you'll see on the left-hand side, data pricing. This is dollars per kilometer square. We'll notice on the left-hand side, if you look at spatial resolution in particular, it's an incredible cost, right? You get increased resolution, you get great deal of accuracy, but however, it's application dependent. Now, if you're looking into the marine domain awareness environment, depending on what we're doing, it may not necessarily be important for us to be developing, satellites with such high resolution. What is important to note is that if you start looking at this particular area at the bottom, right? So we're looking at just over 2.5 to sort of 5 meter resolution. It's an important area in which we need to look into, because that present to us many opportunities. So to demonstrate, these are two sort of payloads we're looking at that are being developed in South Africa. As a demonstration, we've got a particular product which will give you a resolution of 4.75 meters and will fit into a 1.5 view CubeSat platform, 7 bands, multispectral, and 32 bands are hyperspectral. Similar to that, we can go up to 1.5 meters with a sort of 14 kilometers in a 12 view configuration. I think the point I want to make is that in terms of the technology going forward, in terms of our own development, we need to focus on getting a multi-sensor, multi-purpose mission to meet the broader requirements of our user. So I think that sort of concludes my presentation. I'll try to keep it short. I think the main objective is to show that, from a South African perspective, we are dealing with space in a way that deals with our socioeconomic challenges, and we are trying to build our own indigenous capacity in South Africa and collaborating with our African partners as well. Thank you so much.
Well, thank you so much for providing the South African perspective. And I want to pick up on one very important word you said, which is value. And as you rightly said, as many engineers, myself included, we get tied up with the technicalities of it. But it's really, how do we provide evidence-based decision-making tools, particularly for the end user? So thank you very much, Amal. Our next speaker is Evelyn Honoré-Livermore. Evelyn is a PhD candidate at the Norwegian University of Science and Technology in the Department of Electronic Systems and serves as the project manager for HypeSO-1, the university's first 6U CubeSat. Evelyn, we look forward to hearing from you on how we use a system of autonomous agents to deliver ocean surveillance capabilities. Over to you, Evelyn.
Thank you so much. I hope you can hear me all right and see my screen. Our satellite is called HypeSO. You can see its badge on the right-hand corner. It is our first 6U CubeSat, and it has a hyperspectral imager as its payload. I will describe that in a bit more detail soon. We are doing this mission because Norway has a large coastal line, not as large as Africa, of course, but for us, it's really, really long. And most of our population is along the coast. Two of our main industries are also coastal. It's oil and gas and aquaculture. I think about a third of our GDP comes from aquaculture industry, and most of our seafood is exported. Because of that, our university has had a strong focus on the coast and the ocean and learning more. In 2013, we were awarded a Center of Excellence Research called the Center for Autonomous Marine Operations and Systems. It consists of 5 main areas, such as topwater surveillance, underwater surveillance, control of different types of assets, dynamic positioning of ships, communication. And as they were developing this, they also saw that there was a need to build space systems. Because as you mentioned earlier, Amal, You can choose what kind of resolution you want to get depending on what kind of instruments you have or what kind of assets you have. And when we were developing the drone systems underwater, we could get very, very high resolution of very small features. Once you went on water with autonomous surface vehicles, we could get little smaller, little bit worse resolutions, but we could move faster and longer. With drones, you can fly for a couple of hours, perhaps, at an altitude of about 1,000 kilometers, I would say. No, not 1,000 kilometers, sorry. 1,000 meters, 2,000 meters maybe. And if you go up to small satellites or CubeSats, you can have a much larger SWAT area. You can have revisit times of 90 minutes per day. And you can also see bigger areas, but you will not have the ground sampling distance that you would have with your autonomous surface vehicles. So that's how we're trying to like fill the gap with the CubeSat. There are lots of older types of satellites and also newer satellites, such as the Copernicus program, which gives you very, very good spectral, spatial resolution, but very poor revisit time. We wanted to try building our own CubeSat also. We wanted to build capabilities at a university. So our goal was to build a satellite that had improved temporal, spatial, and spectral resolution compared to the Sentinel-3. So that was our benchmark. A $10 billion satellite compared to our, let's say, 100 or 200,000 euro satellite. Hyperspectral remote sensing. If you don't know that, it's when you try to see more than your eye can see. You can pick up bands of spectral information so that you can identify what you're looking at. We joined forces with a research center in Svalbard, which is far up north in Norway, where he had built and designed a hyperspectral imager from COTS components. The design is published. Anyone can build it. You can buy all the components off the shelf and by 3D printing. But we quickly discovered it couldn't give us all the requirements we needed for space. So we had to convert it a bit, still using some 3D printed materials for our prototypes. And for our final system, we're using machined aluminum, but still it's cheap. You can find all the optical components online and get them to your desk in a couple of weeks. Our hyperspectral imager can give us a band resolution of less than 5 nanometers and up to 100 bands, depending on your downlink time. Our mission objective, our mission profile is we have a sun-synchronous orbit, so we will try to revisit Norway and see Norwegian areas at least 3 times a day. By using slewing maneuvers and controlling how the satellite points. We are working closely with the KSAT in Svalbard so that we can uplink the data for where the satellite should look and then take images. We can detect different features in the ocean, and then we can tell maybe drones or autonomous surface vehicles to go there and explore more. The satellite is a 6U CubeSat. We're doing it mostly by buying components from our main provider, Nanoavionics in Lithuania, and integrating it with students, bachelor, master, and PhD students. We are developing solutions for onboard processing to reduce the data size on board so that we can, instead of downlinking a huge hyperspectral image, we can process the data and detect, for example, river runoffs or harmful algal blooms. We are working together with KSAT, which is the largest downlink data provider in the world. And they give us opportunities also to figure out how we could combine forces and combine the data they have access to with our data so we can provide even better warning systems. Other infrastructure or other research projects at our university is the CB. It's situated further north in Norway, and it's all about drones. Andøya Space Center is one of their main partners, which is setting up to be one of Europe's rocket ranges in the next 3 years. Crossing our fingers for that happening quickly. But it also is a very, very large drone test center with one of the largest areas with no one else around and not military. So you can actually go there and figure out how to do drone operations. Partners, we work with the Norwegian Research Council quite closely and the Norwegian Space Agency. We get about 20 students every year. One of our biggest challenges is onboarding and offboarding. We get new students every 9 months. And can you imagine trying to teach such a complex system as space and building CubeSats in a couple of months, and then you lose everyone after 9 months? It is really, really fun, but also very challenging. We're planning to launch next year, but until then, we've done some drone test flights with our hyperspectral imager. We also put the hyperspectral imager underwater, so we could get in situ measurements to confirm what the drone is looking at. We've done field trials outside Barbados with our American partners. And with our other American partners, we've tested our hyperspectral imager in a balloon flight. This summer, our autonomous surface vehicle, which is called Autonaut, went for a 3-week-long voyage alone, autonomously. It has about 9 different scientific instruments, and it's solar powered, so that it can communicate with us, it can take measurements, we can command it where to go. And the goal is that our satellite in the end can tell the Autonaut, oh, you need to go there, explore some more, provide in situ measurements, so that we can learn more, and we can also try to detect all these ocean colors and understand more about our world. Thank you for listening, and I look forward to hearing from the other panelists today.
Evelyn, thank you so much. It really struck me when you were comparing, especially on the budgetary side, the $10 billion satellites compared to 100 or 200,000 euros satellite, and just going through what the capabilities are of your satellite is really impressive, and we wish you the very best for the launch next year. So thank you very much, Evelyn.
Thank you.
Our third speaker is Emory, Program Manager for the Advanced Component Technologies for NASA's Earth Science Technology Office. Amber's presentation will briefly introduce the NASA Earth Science Technology Office INVEST program and the critical need to develop science-driven technologies for CubeSat and nanosatellite missions. Amber, the virtual floor is yours. Oh, Amber, I think you might be speaking on mute.
I am. Thank you. I'm glad I got that. All right. There we go. Now you can see me and hear me. Oh, this new world that we all live in. Okay. So again, I'd like to thank the previous speakers, Amal and Evelyn, for giving a bit of introduction into kind of the CubeSat, and we sometimes call nanosat. I generally tend to think of nanosats as even smaller than the CubeSat. So this is going to give you just a brief introduction of some of the work that we are doing within the Earth Science Technology Office. We could go to the next slide, please. All right, it wouldn't be a NASA presentation if we didn't have an org chart to start. I'll keep this very short. So you can see within the NASA Earth Science Division, there's the 4 areas: flight programs, research and analysis, applied sciences, and then ESTO there in the lower right. And I'm one of the program managers for ESTO. Again, my program is the Advanced Component Technologies, which eventually some of them do make it into the INVEST program. So Sachi Babu is our program manager for INVEST. So I'm kind of standing in for him today, but I do manage another CubeSat within our INVEST program. So we can talk about that too. And if you have any questions on that, we can address later. Okay, next slide, please. So this gives you just kind of an idea of what the elements within ESTO are. So again, ACT and INVEST are in the what we call the Advanced Technology Initiatives program, so they're combined. We have the Instrument Incubator program, IIP, the Advanced Information Systems Technology, where we are really looking at things like onboard processing within CubeSats. So that's more of the software side of the house, as opposed to ACT Invest in IIP. And then we also have from the Decadal Survey, the 2017 Decadal Survey, we have a new program called the Decadal Incubation. And one of those within the planetary boundary layer, looking at air-sea interaction. So we're actually looking at putting together a complete architecture for that mission that is composed almost solely of CubeSats. Okay, go ahead to the next slide, please. So this is just kind of a quick chart on some of our previous projects. So Raven, IceCube, and Murata. So those were some of the early CubeSats. Right now we have 5 that are in primary ops: Qbert, RainCube, Tempest D, CSIM, and HARP, which actually just launched. Those dates on there need to be updated. And then we have Cirrus with the commissioning in process. So I'll show you just some of the highlights here coming up. Okay, if we can go to the next slide. All right, so for example, this is some of the data from CSIM, which is the Compact Spectral Irradiance Monitor. And again, this was a flight demonstration mission, but you can see here we have the first levels of public data release. And this is really going to go forward into the primary goal for CSIM was to demonstrate continuity level science capability in a miniaturized and more cost-effective package. Okay, if we'll go on to the next slide. Here, I want to spend some time more on the kind of air-sea interaction, and also my personal love for tropical cyclones and hurricanes. So we'll get to that in a moment. So recent deployments, Invest 12, the HARP, which is a polarimeter, that launched on November 2nd of 2019. And we had some first light images earlier this year. And on the other side, we have the Cirrus CubeSat, which launched on December 5th. So in our next couple of slides, what I'm going to focus in on here are some of the first light images from the HARP CubeSat. So kind of bringing everything all in together. So let's go on to the next slide, please. All right, so these are just some examples of tying everything all in together. So this is Saharan dust leaving the coast of West Africa. So you can see on the right is the ESA Sentinel aerosol index, and then on the left there you can see the multi-angle CubeSat. So this is HARP, your images from there. And if we go on to the next slide, it's kind of an interesting. So a lot of this is kind of eye candy for what we can do with CubeSats. So you can see here there on the right, there's the HARP multi-angle image of the dust that's actually leaving the coast of West Africa and then arriving over into the Caribbean so it left on June 13th and arrived in the Caribbean around the 23rd, so about 10 days later. So we can actually see this with a CubeSat. Go ahead on to the next slide, please, if you would. And so here's another area of interest kind of within the realm of sea and air interactions, near and dear to my heart, because this is where I spent my PhD work. So we're actually using with Tempest D, which is again another 6U CubeSat, and we can see here this is the larger background image. There is GOES-W visible data from, this is Hurricane Douglas earlier this year. And on the lower left, you can see the animation for multiple levels within the hurricane as it neared Hawaii. And you can see the image of Tempest D with the solar panels there fully displayed. And I won't share it here, but there's some, if we want to talk about that later, we had a really interesting launch from the International Space Station of Tempest D. The solar panels deployed sooner than they were supposed to, but in the end, everything worked out okay. All right, if we go on to the next slide here, there's a little bit more from Tempest D. So again, this is GOES WIR data, again from Hurricane Douglas. And we can go on to the next slide, please. So this is even more recent data. So we have RainCube, which is another one of our CubeSats. It's a Ka band radar. And my background is in radar meteorology. And of course, radar isn't new, but I like to say with RainCube, having a radar in a 6U CubeSat is. So what we've been doing a lot, this is in collaboration with JPL, Colorado State, and Blue Canyon Technologies. So what we've been doing is looking at the radar and millimeter wavelength imaging radiometer data, and you can see that in the animation in the lower left. So these two CubeSats were actually able to capture both Laura and Marco at different stages within the Gulf of Mexico. Of course, at that point, Marco was making landfall, and Laura was beginning to strengthen in the Caribbean. So these are some of the ideas that, some of the technologies that we enable within CubeSats. Okay, if we go on to the next slide. I think here, okay, I'm going to keep it short. I have my 10-minute timer on here. So this is just to kind of give you a flavor of the different types of CubeSat and CubeSat technologies that we're enabling here at NASA ESTO. So what I'd like to leave you with are 3 points here, that the future of NASA Earth science missions could be composed partially, or in the case of a possible future planetary boundary layer mission, or entirely of constellations of CubeSats. And I normally think of those in our 6U to 3U down to nanosats. And there I really think of more on the level of the 1U CubeSats. And we are developing technologies for that I wasn't able to get into today. Second point, NASA ESTO, we are critically involved in developing this science-driven technology for these current missions and ones into the future. And finally, NASA ESTO and NASA in general, we look forward to working with other US agencies, NOAA, DOE, DOD, and international partners as well. So ESA, CNES, and more to make this future reality. Thank you very much.
Amber, thank you so much. And it was really excellent to see the animation of Hurricane Douglas, especially with those different tiers and levels. And I hope in the Q&A time, we get to dig a little bit deeper about those partnerships you mentioned, DOD, NOAA, and other organizations, and how they utilize some of this information and really make one long-term policy recommendations, and also how did they get this information out to the public and support some of their work as well. So we'll dig a little bit deeper into that when we get to Q&A. So thank you very much, Amber. I'd like to remind the audience that there are opportunities for you to ask your questions as well. So on the right-hand side of your screen, you'll see a little chat box. So we're really looking forward to seeing some questions from our audience. With that, I'd like to go to our next speaker, Milton Kampel, a satellite oceanographer working at the National Institute for Space Research in Brazil. in the field of remote sensing of the oceans. Thank you for joining us, Milton. We look forward to learning about the infrastructure available in the areas of space engineering and technology in Brazil, in INPE, and the development of small satellites. So I'll hand it over to you, Milton.
Thank you very much for the introduction, Minoo. I will let me close my video for saving some band from here. Then I will share my screen. Can you see it from there?
Yes, you might want to make it the presenter mode.
Yes, and I will run it. Thank you very much. Hi for all. My name is Milton Kampel, and I'm a satellite oceanographer from Brazil. And first, I'd like to thank the organizer of this event for the invitation to participate in this session on nanosatellites. I work at the Brazilian National Institute for Space Research INPE, which is a civil research institute of the Ministry of Science, Technology and Innovation of Brazil. INPE's priority engagement areas include the United Nations 2030 Agenda for Sustainable Development, the Paris Agreement, and the SEDAI Framework for Disaster Risk Reduction. On September 10th, Ordinance 3446 was published with a new internal regulation for INPE. The former Earth Observation General Coordination and the Weather Forecast and Climate Study Center have joined the Earth System Science Coordination in a new Earth Science General Coordination. Thus, I am currently linked to the Earth Observation and Geoinformatics Division. We had the successful launch of Sibers 4A satellite in December 2019, whose commissioning was completed in August 2020. Images from the MOOCs, WPM, and WFI cameras are generated and distributed routinely with revisit time of 31, 31, and 5 days, swaths of 95, 92, and 684 kilometers, with 4 multispectral bands in the blue, green, red, and near-infrared, with spatial resolutions of 16, 8, and 55 meters respectively. The WPM camera also has a panchromatic band with 2 meters resolution. This mission is part of a family of satellites started with Sibers 1. Here we can see examples of images from the Sibers 4A WFI camera of the coast of Rio de Janeiro, Brazil, acquired on July 8, 2020 with 55 meters resolution. Also from the MOOCs camera of the north coast of São Paulo with 16 meters resolution, and from the WPM camera with 2 meters resolution in a fusion product of the panchromatic band with the multispectral bands of the north coast of São Paulo. And here we have a fusion product of the panchromatic band with 2 meters resolution with the blue, green, and red multispectral bands with 8 meter resolution on July 28, 2020, from the region of Arraial do Cabo and part of the Araruama Lagoon on the north coast of Rio de Janeiro. And here we can see a cargo ship and an oil tanker in the region of the Santos Basin, where Brazil has large oil reserves in deep waters. We are waiting for the launch of the Amazonia 1 remote sensing satellite, the first to use the multi-mission platform developed at INPE, focused on monitoring deforestation and vegetation cover. Due to COVID-19, the launch was postponed to February 15, 2021. We also have more than 60% ready for an upcoming multi-mission platform mission, but still awaiting the definition of the payload. We hope for an ocean observation mission, which could be in the range of visible infrared or in the X-band microwaves. The Laboratory of Integration and Testing contributes to Brazil's progressive autonomy in strategic areas, provide technical support to the efforts of national productive sector in developing its competitiveness in the international market, create the necessary environment for the promotion of national space programs and in cooperation with other countries, providing high-quality services, low-cost and timely, and provide testing and metrology services to the industry. We can observe the experience in assembly, integration, and test of different satellites, not only Brazilian but from other countries and agencies as well, including small satellites. It is worth highlighting the experience acquired in development. The scenario of small satellites in Brazil started with the development of Nanosat BR1 in cooperation with a university from the southern Brazil, followed by another cooperation with the Aeronautical Technological Institute. Other missions followed in collaboration with other universities, institutes, private companies and agencies, both Brazilian and international, including a municipal school, until the first constellation of CubeSats under development. The Floripa Nanosat was launched in tandem with Sibers 4A satellite. In this way, it was possible to develop an ecosystem of small satellites based on principles of research, innovation, and development, involving the academic sector and the funding agencies, integrated with an industrial policy, with a focus on offering services and applications of interest or social benefits. The basis for the production of small satellites at INPE involved the conceptual architecture of a standard space mission with all segments and components considered important, as well as the life cycle of a complete space mission. INPE only does not develop the launch vehicle, and since Brazil does not yet have satellite launchers, we hire commercial launchers or reach the space through international collaborations. The requirements of small satellite projects and programs demand a mapping of stakeholders, a diagnosis of as-is, the strengthening of themes considered essential, and planning of how to be. Technological challenges are identified and addressed, considering the development needs, what data is being demanded by different areas, and whether there are technologies to be validated. The ground segment has tracking and control facilities at INPE's headquarters in São José dos Campos, in Cuiabá in central Brazil and also central South America, and in the northern region on the equator at Alcântara. It also has infrastructure for receiving and storing satellite data in Cuiabá and Cachoeira Paulista, which is 100 kilometers from São José, where INPE maintains its Cray XC50 supercomputer and a remote sensing data center with 6 petabytes. In terms of proposals for advancing small satellites, we must consider the training of young people and others interested in entrepreneurship. One idea would be to create a center for incubation of technology-based companies on nanosatellites. From there, it would be possible to offer technical support, mentoring, networking, training and qualification, and transfer of know-how. Finally, we must consider the creation of demands in its sector. In addition to actions such as Cube Design, with its 4-edition schedule at INPE to 2021 and collaboration models, it would be important and interesting to participate in mission programs such as the constellation proposed by their center to leverage the development of Earth observation nanosatellites. In any case, it is necessary to define the payload or the type of instrument of a mission. So, as a suggestion, why not an hyperspectral nanosatellite? In this case and in our context, what would be the problem to be addressed? Resolve the complexity of coastal waters. Extensive studies using in situ measurements and remote sensing imaging have shown that visible hyperspectral imaging is one of the best available tools to resolve the complexity of the coastal ocean from space. There is a need for high spatial and temporal resolution in the near coastal ocean. What we need to solve this problem? A stable, well-calibrated sensor with high signal-to-noise ratio, good characterization and calibration, atmospheric correction, in-water algorithms to solve for water column optical properties, bottom type, and bathymetry. I'd like to thank my colleagues Antônio Carlos Pereira. I'd like to thank my colleagues Antônio Carlos Pereira, Head of Small Satellites Division, Ivan Barbosa, Data Infrastructure and Supercomputer Coordinator, Mauricio Ferreira, Satellite Tracking Control and Reception Coordinator, Laércio Namikawa, and Walter Abraão for sharing materials and information. I also thank everyone for the audience, and I'm available for questions. Okay, Dan. Thank you very much.
Milton, thank you so much for that excellent presentation. You mentioned a few things that I want to jump on. One is the entrepreneurship training and leveraging nanosatellite R&D. I think those are really fantastic initiatives. Thank you for talking a little bit more about INPE and providing us with a background on that. And I think that in the audience Q&A, we can definitely also, between Evelyn and yourselves, talk about hyperspectral nanosatellites. So looking forward to getting stuck into some of those questions. Again, I want to remind the audience to ask your questions. We have a fantastic group of panelists here that represent government agencies, but also academia and organizations as well. So ask those questions. You have a chat box on the right-hand side of your screen. We have a couple of questions coming in. So maybe, Amal, I might ask you first. So we have a question from the audience that says, how do you translate local needs of coastal communities in Africa, particularly thinking of small islands that may surround the African continent or part of the Africa, such as Cabo Verde or Mauritius and things like that?
I mean, thanks for that. I think what's important to note is that, all space-related activities are essentially driven by a broader user community. In South Africa in particular, and our focus at the moment is obviously South Africa, our key objective is for us to provide the necessary services and applications that meets the needs of the challenges that we face as a country. What we are trying to do at the moment is extend our relationship with other African countries. So in terms of partnerships and collaboration, it becomes important to listen to smaller countries, islands, to try and understand what are their needs. Even if you look at the presentations today, you'll notice that everybody's doing very interesting. So turn on my video. Sorry, I didn't realize it was switched off. Yeah, everybody's doing very interesting research, right? We're all trying to develop similar technologies. We're all trying to solve, problems that will essentially ensure that we have a sustainable planet at the end of the day. So really, I think from our perspective, there are various strategies that are being developed. We at the agency are currently working on a SEDEC strategy. So if you take the whole African space strategy, there's the north side and the south side and the east and the west sort of. And within those sort of domains, there are user groups that are being developed to understand what is the need on the south side of Africa, right? So these are smaller teams collaborating together. And essentially you have four big sort of, regional, continental sort of areas that will start a dialogue to understand what these needs are. I think it's only through the dialogue of engaging we better understand, the mission requirements and the needs of other countries as well. Thank you.
Amal, thank you so much. And, in your presentation, you also mentioned the African Space Agency, which is a continental space agency that looks at gathering 54 member states in Africa under one umbrella agency. So really linking the capabilities of African member states, I think, is so important, and that sharing of knowledge and capacity building, as you rightly mentioned. So thank you very much. Evelyn, I might hand over to you. when you talked about your presentation, you talked about one of the challenges being that you had a number of students coming in and then leaving, and so it was, starting from scratch sometimes, or making sure that there was a strategy of lessons learned between your cohorts of students. I was wondering if you could talk a little bit more or elaborate on some of the challenges you are finding as a university who's developing their first 6U CubeSat.
Thank you for that question. It's a bit different than what I expected. Well, first of all, when we get our new students, we try to get them to understand what our stakeholders need. So we do the simulations where they pretend that they are the satellite on top of a roof in our university, and then they pan the ocean and they take images, and then they process the data. Because we found that giving them hands-on experience with flying a satellite from the roof is the closest we can get for them to understand all the technical difficulties and to understand how they fit into the organization. We struggle with figuring out a good way of documenting the knowledge. To do hyperspectral image processing, I think Mr. Kampel mentioned it, it is very, very difficult to account for all the atmospheric corrections that you need to have, or sun glint, or waves even. So our software group is probably 70% of our people at all times, meaning that if every student, even the mechanical students, get experience with taking an image and trying to understand what they're looking at, they also get an understanding for why it is important to have temperature control, to have a telescope that doesn't move if one side of a CubeSat is warmer than the other, and then to work together with software to understand their difficulties in doing the processing, what they need, if they need better stiffness, for example, between the GPS antenna and the camera itself, which can help them process. That means the mechanical team needs to make the mechanical stiffness better. So we're trying to do more hands-on experience early before it gets too dark in Norway and they can't really take pictures outdoors. And we found that it helps, but it is a challenge every year, and everyone is different. Everyone has a different background. Corona was a challenge, but the one thing that I found very impressive among our students is that they're so willing to try new things. I think it was one day they were negative, and after that they were like, yay, online all the time, want to work on Slack, want to be on Zoom. It was amazing. I was really, really impressed.
Yeah, thank you so much for elaborating more on that. It's incredible how the next generation has this vast enthusiasm, and then they have so many different ways of overcoming some of the challenges that we might find as larger hurdles. But yeah, thank you so much. I have a question here from the audience from Nuno Morina for Amber. So Amber, Nuno says, is data from RainCube and Tempest-D satellite being used at the National Meteorological Service in current operations? And if yes, how is that being so?
Hi, thanks. That's a great question. So for right now, in the INVEST program, we push more for the validation of technology. So in real time, we aren't there just yet. I will say that NOAA is very, very interested in this technology. So we actually had another program that started, or another project that started under INVEST called Cirrus, that was a hyperspectral sounder. And we do have, the INVEST program is somewhat small, and as the project progressed along, what we saw was that they were going to be really running over budget, and that got them outside of the cap of where we needed them to be for on the NASA INVEST side. However, NOAA has actually taken over that project, and they're moving that forward because as we kind of all realize, having a hyperspectral infrared sounder is of real interest to weather forecasting and being able to assimilate that data into models. So INVEST, I would say, is really kind of at the early level, and as you can see, we're not in the constellation stage yet. We do have a couple of projects that are in the IIP program that are looking at this formation constellation flying. So we're very much on the kind of early level in terms of technology development. But again, the end goal, I would say, I wouldn't even put it at 10 years. We're probably around the 5-year or less mark for having these data assimilated in real time into models. So that's what we're working on. That was a great question, though. Thank you.
Fantastic. Thank you, Amber. And you answered the second part of the question, really, which was, is this data envisioned to be available in real time? And I know, again, talking about the partners that you worked with, the closer it is to real-time data, the more valuable that data is. And of course, historical data also allows us to capture key trends, but having that real-time data is crucial. So yeah, thank you so much, Amber. It's great to hear that the timeline really is so short. Milton, I have a question here from you for the audience. You talked about entrepreneurship training, and everybody now is starting startups, and there's this vibe of innovation and entrepreneurship that's really very global. One of the questions from the audience is, how do you have local workshops or any larger consultation processes that will spur on entrepreneurship and innovation? Oh, Milton, you might be talking on mute.
You're right. Sorry for that. I was saying that this could be a long story. I will try to make it shorter. And for now, I think that the CubeSats and nanosats, or small sats in general, they started, at least in Brazil, as educational programs, making the access to space more democratic somehow, and also taking the momentum of the innovation and technological developments from the universities. And as a research institute in the space industry, we've been trying to collaborate with them, but also joining with the previous questions that Amal answered, is always tricky to decide to put the infrastructure we've built in the last years for building other satellites, bigger satellites, for building small satellites. Considering all the engineering processes we still follow, even for doing small sites. But young people, they are, part of this since the very beginning, and you have been promoting cube designs, workshops, even ArtSat initiatives, and trying to promote entrepreneurship from them. And this is in line and is part of all this development. However, when we're really looking for scientific or more operational applications, as Evelyn was mentioning, it's not that tricky to have all the eggs in the same basket. But as you can see, NASA is doing that. And also ESA have been promoting quite a lot of initiatives more recently, and also South Africa. And what happens is that I can see is that there are still some requirements. And for example, I see that as in US, you have a science-driven missions. In ESA, you have a kind of an end-user-driven missions. But like in Brazil and maybe other countries, sometimes it's very much related to technological development. So must be a balance, and that's why you need young blood, young people, and entrepreneurial startups taking part since the very beginning. So those are my 2 words about it. Thank you.
Thank you, Milton. And I hope with your words, you've also inspired a few people from our audience as well. So thank you very much for that. Evelyn, I might go back to you. We have a question from the audience from Stuart Bernard. How would you see the next steps around creating a collaborative constellation, for example, around hyperspectral? Could we work towards maybe establishing minimum mission requirements?
Thank you for that question, Stuart. It's actually something that we have been discussing within the AIR Corporation framework. When we first did our mission objectives and mission planning, we tried to determine how many hyperspectral satellites we would want to fulfill our needs. Our goal is, of course, to take over the world and have 20 or 30 satellites so we can have high temporal resolution. We cannot afford that as a university, but maybe a company would be interested in doing that. But putting that to the side, what we find challenging still is not only to have the collaborative constellation, but actually being able to have good methods of data processing. For every pass, we would get gigabytes of data, which is a lot to downlink for a CubeSat. If you have a constellation of CubeSat that are imaging several times a day, you need to find even better data fusion algorithms and better AI processing algorithms that are in situ validated. So I think what we would need to do is to see what did, for example, the Northern Hemisphere and the Southern Hemisphere have of scientific needs, both for what kind of spectral resolutions they need and what kind of sensitivity you have. There are very different sensitivity requirements for ocean or on land. And then maybe work together in workshops and find the optimum balance for satisfying those needs in a timely manner and getting the constellation off ground. And then work together with data processing companies and also KSAT, for example, or other downlink services to be able to downlink this ginormous amount of data you will get. Or in parallel, also develop AI edge computing capabilities so that you can do processing on board the CubeSat. For example, by having deployable solar panels, so you get more power and energy in the CubeSat. But it is very challenging when you have the hyper instead of the multi we found, because the data amounts are so large. As Amal Khatri says, the AIR Corporation, they have done a very, very good job at looking at requirements for the ocean needs. And I think building on that and also building on all the previous scientific papers on what you need for ocean color and land color for hyperspectral imaging would really be a good starting point.
Evelyn, thank you so much. I think we can have a whole nother panel just talking about that one particular question. But I'll throw it back to Milton. Milton, you talked about some of the challenges of hyperspectral. Do you have any comments to add to that question?
Yeah, I agree very much with Evelyn, and also I like to see the question from Stuart that, I mean, at least minimum requirements, they would be, I mean, a good practice. Let's talk about good practice for working in a collaborative way, because, I mean, this is very democratic. So as I mentioned in my presentation, we had a municipal school building a CubeSat. They bought the kit from the open shelf and the market, but it didn't work. So they came to INPE and had to rebuild everything and spend a lot of time, even some funding, and to have it properly working and it's flying, and they're happy with that. But so it still requires time and some funding, even it's very much affordable. So I think that we should try to do our best, what is available. And as I mentioned before, this balancing between science-driven or end-user-driven versus technological development is that as you've been doing much more of not small satellites. And so our engineers, they are always saying that maybe technology is not mature enough. But what you can see from very examples, that is becoming more and more. So it's the same story as digital cameras, smartphones, cloud computing. So the future is now.
Well said, Milton. Thank you very much. Amber, I might come to you. You talked about collaborations and corporations. I was wondering whether you could elaborate a little bit more about what that actually looked like and provide an example of how you work with other groups to either assess or analyze data or get this data into the hands of other departments and other organizations.
Okay, thanks for that question as well. So we have things like MOUs, or we always talk in acronyms at NASA and government agencies, it seems like. So that's a memorandum of understanding. Actually, right now, as an example, we are working with NOAA, and to the level where we have the legal teams from both headquarters going over documents so that we can kind of make a little bit more seamless. So we can have program managers such as myself talk with folks at different agencies, but this is really a way so that we can start sharing knowledge between the agencies. Again, it is in its early stages, but really here we kind of see NASA as the start. We do the tech development. That is what I'm involved with day in, day out. I eat, sleep, and breathe technology development. And so again, as you see at ESTO, we're really kind of pushing on the early levels to show that tech validation to be able to do science and get data from space. So some of our early missions, it was just we send up the instrument and we see if we can turn it on and it works. And you can see one of our early missions, Marada, we tried multiple times. And so, but those are sort of the growing pains that we go through to be able to show that we can launch a CubeSat and then hopefully into the future doing something where we could launch, one or multiple or 10. So we've honestly started looking at that, but it's really a larger solution than just NASA alone. So we can kind of push, at the front to show that yes, we can do this technology validation in space, but we do need to work with folks like NOAA, and the U.S. Air Force is interested as well in what we're doing. And we also, I like to come over for Living Planet. I was over there, I guess that was in Milan. I think that was 2018, I think it was. So we like to reach out, and I think this is a great area here. I've have some new contacts and folks to talk with about how we can really start looking at CubeSats and how we can push. I do agree that the future is now, and I think within the next 5 to 10 years, we're just going to completely change what constellations of CubeSats. We don't have those yet, but they're coming. So I hope that answers the question. We've got the MOUs, legal teams to kind of open the pathways for discussion. Thanks.
Yeah, thank you so much, Amber. And I will say through all of your presentations, all of you have talked about collaboration and cooperation and partnerships. And it's great to see that even though our panelists are from different countries and different regions, there's that underlying sense of collaboration. And as Amal also pointed out, it's important to collaborate within the Air Center Corporation framework. Great. Amal, Milton, I have a question from the audience for you, from Marcelo from Brazil. He says, great presentation. Does INPE work with INPO, INPO, in regards to coastal and ocean observation?
Okay. So thank you for the question, Marcelo. Let me tell the audience that INPO was an acronym for a proposed Brazilian National Institute for Oceanography, but it does not exist for real yet. But as we are under Ministry of Science and Technology, we're supposed to be at least participating in those discussions, although this is not the present situation. So we are following the news about what could be the Brazilian National Institute of Oceanography, maybe, I mean, very from far. So I cannot add very much about it, unfortunately. Although I would be very supportive for that. As an oceanographer, I'll be happy to collaborate and to work together.
Thank you, Milton. Our last question is to Amal. We ask, how are there ethical concerns such as privacy and security that should be considered when we think about Earth observation and remote sensing that we're deriving from CubeSats and nanosatellites? And how do you work with the end users to ensure that that privacy concerns are catered to?
Okay. Yeah. Okay. Minoo, thanks for that. I think privacy is always a concern. And I think if you think about satellites, you know, they sort of keeping an eye on us out there in space, and there's lots of information, or rather data, that we can process, and you know, there's obviously very interesting information you can get out of that. I think, you know, when it comes to constellations and space missions, it goes back to the requirement of the user. You know, you're designing fit for a particular purpose. In terms of developing the mission going forward, these considerations have to be taken into account. So from a systems engineering perspective, when you're designing these missions, you are looking at it at a holistic way. So you're not only looking at, you know, the data requirements, but you're looking at as well as the security requirements. It's also the access to the data. You know, who's collaborating on the program itself, right? Is there sensitive information that could, you know, compromise any one particular entity? These are some of the delicate collaboration and partnership discussions that need to happen. Particularly if you're collaborating with a number of different parties, there's always sensitivity in terms of, you know, what we're sharing. And the accessibility of the data, which is primarily the biggest concern, is that even if you collaborate with various partners, on what platform is this data available? You know, is it available in the public domain? Is it available on the cloud, for instance? And what mechanisms we put in place to ensure that there's a certain level of integrity in the cooperation between various entities. So it's not, you know, it's not a simple answer. I think what we need to do is we need to clearly define the rules around, particularly around collaboration and partnerships, because every organization have a particular need. There's always some level of decision making and a high level of cooperation that's required, and to foster the relationship. Quite often the difficulty is not necessarily the technology we're developing, you know, but, you know, the legal framework under which we're operating, the intellectual property, for example, that we are developing. You know, what's going into the satellite, right? Are we all aware of what we're developing? Do we understand what the payload does? Do we understand, you know, what sort of security measures are built into ensuring that the information that we retrieve into our ground station is adequately managed, you know, throughout the value chain of the space system. So yeah, it's not a, you know, a straightforward answer, but I think what's important to consider is that there are various elements that we need to take into consideration when we develop these partnerships going forward.
I think that's very well said, Amal. Thank you so much. I often say that sometimes the regulatory and the legal framework doesn't always keep up with the technology. And I think that we need to make sure that, you know, both sides are talking the same language. So we're making sure that when we are designing these technologies, we're also taking into consideration how the data is being used and the legal side of that as well. So thank you. So we're at the end of our panel, and it's about time to wrap up. I firstly want to thank all of our fantastic panelists for providing their perspectives. As I said, whether it be an agency perspective, an academic perspective, or a research organization. And really, you can tell from the panelists we're from all over the globe, and yet there's so many similarities in the trends that we're seeing with respect to this topic. I also want to thank Penn State's Alliance for Education, Science, Engineering, and Design with Africa, and also the Air Center for putting this together. I want to thank the audience for asking some really fantastic questions and helping us knuckle down in some of the more important topics. And we hope to continue this conversation with all of you. As Milton very nicely said, the future is now. And with the help of nanosatellites, we are seeing ways that technology can help us with some of the challenges related to our coastlines and water, but also our environmental challenges by providing us with unique data points that really blend quite well with in situ measurements. So with that, I want to thank everybody, thank our panel, thank our audience, and thank our organizers for putting this together. This is one of the last panels before we wrap up officially. So with that, I thank everybody, and I hope to see you soon. Keep well, stay healthy, and in good spirits. Thanks, everyone.